Today we're going to do two sections because they're kind of easy. We're going to do lines and planes. In 2 dimensions with algebra, we always found we could write simple equations for lines like y equals mx plus b for any non-vertical line. Give you a y-intercept b and a slope, rise over run m. And the single equation worked very nicely, but in 3 dimensions we run into a problem. We can't just use z equals a number times x plus a number times y plus a number. We might think this is looks like a linear equation like this one. It is called a linear equation, but the equation is actually of a plane, it turns out. We'll do that later in the lecture today. But what we need instead is this. We're thinking of taking the x-axis, or let's call it a t-axis, and mapping that t-axis into points all along a straight direction. So we consider this. I'm going to do it in 2 dimensions first, and then I'll move over to 3 dimensions. Because I could have also done this one this way. Suppose I had any point whatsoever on a line, x0, y0, and any other point, x1, y1, 2 distinct points determining an equal line, right? And I could think of this line as being the sum of this vector from the origin, which then, since it goes from the origin to this point, has the components equal to these coordinates, x0, y0, and then move along this line some multiple of this vector going from x0, y0 to x1, y1. So if I call this point P, and I call this point Q, then what do I want to do? I want to take the vector from the origin to P, and then from P to Q, and I could take some multiple of it. In general, I might go from, I want to get to this point over here. How do I get to that point? I could say the end of this vector, R, let's call it a function of t, is PQ, well, let's call this R0, goes to the point x0, y0. I'm sorry, so OP is x0, y0. And then PQ I'm going to call V. And if I were to take and want to get to this point, I know there's the vector R0 plus somewhere moving along here, some multiple of V, T, gets me to the point that I want over here, any other point on the line. And by letting T vary over all real numbers, I can go as far out in this direction or as far out in this direction as I want. By any point here, I can get by going up here and then moving along this, some multiple of this vector. So that's how we're going to write a parametric equations for a line in 2 dimensions and then extend it to 3 dimensions. Hence, we could write, well, if R of t contains your position, x of t, y of t along the line, so we're going out to some point here, x of t, y of t. We can get to it by taking the point x0, y0 plus t times this vector here. Let's give v components, oops, red I guess, a, b, and so I can get to any point on the line by writing the x and y coordinates as a vector of this point plus an arbitrary multiple of a vector of this vector v with components a, b. So this is called the vector parametric form for a line. take the individual components. Two vectors are equal if and only if their components are equal. If you rewrite equivalently, x of t, or just x, is equal to x0 plus at. Y is equal to y0 plus bt. Equating the components, we call these parametric equations for the line. What line is it? Well, it's the line through x0, y0 going in the direction of AB, so we'll just call it that. It's the line that contains x0, y0 and is parallel to AB. That's no big deal in the plane because you could have written y equals mx plus b form instead, but we'll now say similarly in 3 space, 3 Euclidean dimensions. We can draw the same kind of picture. Here's x, y, and z. And if we want to sweep out a line, now we can take a point x0, y0, z0 with r0, the vector to that point. And then if we take any vector, any non-zero vector whatsoever, v with components a, b, c, we can get to any point, an arbitrary point of a line, x, y, z, or let's say this is the vector x, y, z. The terminal point of the vector sweeps out the line is the idea, is equal to x0, y0, z0, plus some multiple t of a, b, c, and this is vector parametric form for the line through x0, y0, z0 in the direction a, b, c. And then you can write equivalently by equating components once again. X equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct, 3 parametric equations where t is called the parameter and runs from minus infinity to infinity. And the idea is you're in one-to-one correspondence between the t-axis and the points here moving along the line. So this is what you need, is the parametric form and the vector parametric form, both in 2 dimensions and in 3 dimensions. That's how simple it is to write equations for a line. Now we just want to be able to do some problems with it. Here's how easy the first problems are. Suppose I asked you to find parametric equations for the line going through the point -1, 2, parallel to the vector 5, -4. All you do is write this. You say this is A and this is B. This is x0 and y0. Parametric equations are x equals x0 plus at y equals y0 plus bt. There's parametric equations for that line in the plane. Let's bring up the book here. So here's what the book says for parametric equations for a line in the plane. X equals x0 plus at, y equals y0 plus bt. In free space, those two plus z equals z0 plus ct. And you can do that in 2 dimensions or in 3 dimensions. Here, let's do example P just off of the book. Suppose I want the plane, the line that passes through 1, 2, minus 3, and is parallel to the vector 4, 5, minus 7. Well, you just put 1, 2, minus 3, 4, 5, minus 7. The components of the vector all multiply t. The point coordinates are all constants, and you just get x0 plus at, y0 plus bt, c0 plus ct. Here's a nice example here. Find parametric equations for the line passing through these 2 points. This is a common problem, right? In Euclidean geometry, 2 distinct points determine unique lines. Euclidean geometry is in a plane, but we can extend it to 3 dimensions now. And we say, how do we do that? I know a vector that goes in the direction from point 1 to point 2. You just subtract the coordinates, right? 2 minus 5 is, let's do it the other way. 5 minus 2 is 3. 0 minus 4 is negative 4. 7 minus a negative 1 is 8. When you subtract the coordinates, P2 minus P1, that gives you the vector in the direction from P1 to P2. That's this notation. Now I have a vector parallel to the line. I also take either one of the points. Let's take this one here, 2, 4, minus 1. I get x equals x. You put the coordinates of the point first, 2, 4, minus 1. And then the direction components multiply t. 3t minus 4t, 8t. So x0 plus at, y0 plus bt, c0 plus ct. It's as easy as that to write parametric equations for a line in 3 dimensions. Much harder, right? You can't just write a single equation for that, but these parametric equations are nice and easy. So that's a very common problem. If you see 2 lines like this, you can immediately tell things like, are they parallel? You can look at the equations and tell their direction immediately because it's just the numbers multiplying t. The direction of this line is 4 minus 4, 5, right? The direction of this line is 8 minus 3, 1. If one of those vectors is a multiple of the other, then they're parallel. If not, they're not. Well, this component is twice this one, but this one is not twice this one, so they are not parallel vectors, the direction vectors for these 2 lines, hence the lines are not parallel. So you can look at the equations, just compare the things that multiply t, see if the components multiplying t here are a multiple of the ones on the other one, to see if they're parallel. Then you can ask, do they intersect? Well, to check if they intersect, what you can do is set them equal. You want the x coordinates equal and the y coordinates equal at the point where they meet, and then you can find from that what t is by setting those equal, and then see if plugging in t makes z also equal is one way to do it. So we need to satisfy both these equations. We'll change the parameter t. They don't have to have the same t value where they meet, so we'll say in this one let's replace t with t1, and this one let's replace t with t2. And now I want the x and y coordinates to be equal here, let's say. Then I want 1 plus 4t1 equals 2 plus 8t2. I want 5 minus 4t1 equals 4 minus 3t2. These are 2 linear equations, right? 1 plus 4t1 equals 5 minus 4, equals this one, equals the other x coordinate, 2 plus 8t2. And then the y coordinates equal 5 minus 4t1 equals 4 minus 3t2. Two equations and two unknowns, t1 and t2. I can write those equivalently. Let's put them up here. Let's see, if I subtract this over, I get 4t1 minus 8t2 equals 2 minus 1 is 1. And this equation says minus 4t1, subtract this one over, plus 3t2 equals minus 3 minus 5 is minus 8. And to make those, to solve these equations, I can add a multiple of one equation to another. If I call this equation 1 and this equation 2, I can now, in this case, just add 1 times 1 plus 2 and cancel the t1s, right? Now I get, if I add 1 and 2, and generally add a multiple of 1 and 2, that eliminates t1 over here, and then I've got minus 8t2 plus 3t2 is 5t2 equals this one plus this one equals minus 7. So apparently t2 has to be minus 7/5. I now put that into either equation to find out what t1 is. So let's, doesn't matter, let's say in this one, minus 4t1 plus 3 times minus 7/5 equals minus 8. Putting it into the second equation tells me that minus 4t1 has to equal, let's see, 21/5 minus 40/5 is minus 19/5. So t1 has to be 19/20. Now you can just plug those into both things for z. Plug t1 in here and t2 equal here and see if the z coordinates are equal when the x and y coordinates are equal. So this is the t1 and t2 that makes the x and y coordinates equal. You solve for those. Let's see. Well, they did it slightly differently in here, but what you do is you find out that when you plug these values of t into the z coordinates, where the x and y coordinates are equal, the z coordinates do not equal each other, and consequently, the lines do not intersect. So what you do is you just set the x and y coordinates equal, two equations for two unknowns. You generally get exactly one solution. For t1 and t2, you can plug in to see if the z coordinates match. All right. Here's the vector equations of lines. We said you could also write them in this form: xy equals x0, y0 plus t times ab, and in 3 dimensions similarly with one more component. So sometimes we prefer that vector parametric form, written as r equals r0 plus tv. It's just more compact. It's a nice way that works. I want to make one more mention of line segments is coming up here. I guess there it is. Must be here. Let's do one more thing. On this problem, it says find the equation of the line in 3 space that passes through these 2 points. Let's instead find the line segment that passes between those 2 points. We take the vector from P1 to P2 by taking their differences. P2 minus P1 is 5 minus 2 is 3, 0 minus 4 is minus 4, and 7 minus a negative 1 is 8. So here is the direction vector V. And then I can take either one of those points and write this in vector parametric form. R0 will have these coordinates, goes from the origin out to this point, 4, 2, minus 1. And then any point x, y, z in the plane that's on the line can be written as the vector to point P1, 2, 4, minus 1. You also put P2 here, it works just as well, plus t times the direction vector P1, P2 between them. There's the equation for the line, but here's what I wanted to point out on this one. Not only can you do this in 3 space as well as in 2 space, but if you restrict t to be between 0 and 1, what happens? Now when t equals 0, you get just this, the first point. When t equals 1, you get the first point plus t times. This is the vector from P to Q. Alright? This is the vector from the origin to P, plus 1 times the vector from P to Q when t equals 1. So when p equals 1, you go from the origin to P, OP, and then you add the vector from P to Q, and you go from O to Q. And so when t equals 1, it takes you to the point Q. When t equals 0, it takes you to the point P. This sweeps out precisely the line segment from P to Q when you make this direction vector, V, the vector from P to Q, and let t run from 0 to 1. Oops. That's really all there is to lines. They're not very hard. Go on to the next section, talk about planes a little bit. This is nice and very visual also. Let me go back here. How do we write an equation of a plane? Turns out a plane can be written as a single equation. You don't have to write parametric equations for it. Imagine this in 3 dimensions. I take a point on a plane, and I take a vector that's perpendicular to the plane. Let's call it n for a normal vector. And suppose this normal vector has components a, b, and c. And the point here has coordinates x0, y0, z0. So it's kind of like making equations for a line. You need a point and a vector again. But this time, the points of the plane, instead of being along the direction of the vector, I take any point x, y, z in the plane, and the vector from x0, y0, z0 to any point x, y, z in the plane has to be perpendicular to n, the so-called normal to the plane that's perpendicular to every line in the plane. So we can define planes that way. Now how do we do this? We simply say that the points x, y, z in the plane are precisely those satisfying the vector from here to here, x0, y0, z0, to x, y, z. It has components x minus x0, y minus y0, z minus z0. That's this vector here. Must be perpendicular to n, a, b, c. Perpendicular if and only if the dot product is 0, right? So there's the equation for the plane. ABC dot x0 minus x0, y minus y0, z minus z0 equals 0 is an equation for a plane. If we just multiply that out, equivalently we get this times this, a times x minus x0, plus this times this, b times y minus y0, plus this times this, c times z minus z0. equals 0. This we can call equation 1. This is called the point normal form for the equation of a plane. With normal ABC and point x0, y0, z0. It's analogous to what you did in algebra, where you had slope-intercept form of the line in the plane, because m was the slope and b was the y-intercept. You had point slope form, y equals m, y minus y0 equals m times x minus x0. Given a point and a slope, you can write down immediately the equation of a line. Just so here, given a point and a normal to the plane, you can immediately write down the equation of the plane. So this is like that. If you want to write an equation for a plane, you try and find a point on it, and you try and find a normal to it, and then you can immediately write the plane equation. Now, also, by multiplying out, this is ax plus by plus cz minus ax0 minus by0 minus c00. Now, if I add them all over to the other side, it becomes ax0 plus by0 plus cz0. This is another way we could write an equation for the plane. And recognizing that this all just adds up to a number, we could call that d, and we could say, and here's another way to write the equation of a line that's equivalent to the point normal form. And any plane now can be written in this form, and anything in this form can be put back here. And so the standard form for an equation of a plane, actually, remember in this book they put d on the other side. Let's call this minus ax0 plus by0 plus cz0 equals 0, and we'll call all this with the minus sign plus d, and we'll write it like that. Ax plus by plus cz plus d equals 0 is the way this book writes it. Some people put d on the other side. So the standard form for a plane is ax plus by plus cz equals d, with a, b, and c not all 0. Otherwise, this can't be it's just the normal vector just be the 0 vector, right? So a, b, and c not all 0. This is like the general form of an equation for a line. There you said every line can be written as ax plus by. Remember this one? Every line in the plane can be written in this general form. There's the general form of an equation for a line in the plane. Oh, I'm sorry, my camera dropped out. What I was trying to say is that just like ax plus by plus c equals 0 is a general form for all equations in a plane with a, b not 0. It's always a line. Every line has that form. Similarly, ax plus by plus cz plus d equals 0 is a general form for an equation for a plane. Every plane has that form, and every equation of that form with a, b, and c not all 0 is a plane. So we can do a lot of problems now with that. Here's a real simple problem just to start. Suppose I want to find the plane that goes through a point and has a particular normal vector. That's exactly what I need, right? I have the point normal form. I simply put a, b, and c, x0, y0, z0 into the point normal form. A, b, and c go here, x0, y0, z0 go here. A times x minus x0 plus b times y minus y0 plus c times c minus z0 equals 0. You just put them straight into the plane, just like plane equation, just like if you had a slope and a y-intercept, you put in y equals mx plus b because you have the slope m and the y-intercept b. Similarly here, if you have those 6 numbers, you just immediately write the plane. But then that's not really good enough. Usually what you do is you multiply these all out. 4x plus 2y minus 5z plus minus 12 and 2 and minus 35 gives 25, and you get overall 4x plus 2y minus 5z plus 25 equals 0. Just like in algebra, you'd put in the point-slope form, given a point and a slope, and then you'd simplify it to y equals mx plus b form. Similarly here, you start with slope normal, point normal form, simplify it into this standard form. Usually it's simpler to write it down that way. So there's the equation of the plane that goes through the given point and has the given normal vector. Here's the theorem we just wrote about the general standard form for an equation of a plane. Because we derived this from the point normal form where a, b, and c were the coordinates of the normal, you immediately infer what the normal vector is of this plane. It has components a, b, c, or any multiple thereof, any non-zero multiple. So, you can do something like this very easily. Are these planes parallel, I wonder? All you have to do is see if each number here, if you write down the normal vector for this one, just are the coefficients of x, y, and z. 3 minus 4, 5 is the normal to this plane. Minus 6, 8, minus 10 is the normal to this plane. Since the normal here is just minus 2 times the normal here, right? 3 times minus 2 is minus 6, minus 4 times minus 2 is 8, 5 times minus 2 is 10. The ABC here is just times minus 2 just gives that one. The normal vectors are parallel, therefore the planes are also parallel. So that's how you check for parallel planes, is if their normals are parallel. Here's an interesting problem. Suppose you want to find the equation of a plane through 3 points. Just like 2 distinct points determine a unique line in Euclidean geometry in the plane, 3 points not all on a line determine a unique plane in 3 space. And here's how you can derive what it is. You take the 3 points and take the vector from P1 to P2 by subtracting the coordinates. 2 minus 1 is 1. 3 minus 2 is 1. 1 minus a minus 1 is 2. So this is the vector right here that goes from P1 to P2. Then you take the vector from P1 to P3 by subtracting components. 3 minus 1 is 2. Minus 1 minus 2 minus 3. 2 minus a minus 1 is 3. And so you get this vector from P1 to P3. These vectors both lie in the plane, so how can I, on all these problems I think, how can I find a normal and a point? Once I have those, I write down the point normal form, multiply it out in group-like terms to put it in the standard form. So here what I'll do is I say these two are in the plane, 1, 1, 2, and 2 minus 3, 3. If I take their cross product, I get a vector that's perpendicular to both, hence perpendicular to the plane. So I take the cross product as the determinant to compute it. 9, 1, minus 5 is a vector perpendicular to the plane. That, together with any one of the 3 points, I can write in the point normal form. So I take the coefficients 9, 1, minus 5, put those in for A, B, and C in the point normal form. A times x minus x0, I take the first point, let's say. You can take any one of the 3 you want. Plus B is 1 times y minus y0. Let's see. Oh, sorry, it's this one. Y minus y0 is 2. Plus z minus c minus 5 times z minus c0 gives the equals 0, gives the equation of the plane. Multiply it out in group-like terms, you've got that equation. Here's a good one. Wonder if this line, given parametrically like this, x0 plus at, y0 plus bz, bt, z0 plus ct, that's an equation for a line with direction 8, 5, minus 1, the coefficients of t, and through the point 3, 4, minus 3. I wonder if that line is parallel to this plane. How can I tell? Well, it's parallel to the plane if it's perpendicular to the plane's normal. So, here's the plane and here's its normal. A vector parallel to the plane will have to be perpendicular to the normal. So I say, what's the normal of the plane? I could read it off. A, B, and C. 1, minus 3, 5 is a normal vector to the plane. There it is. The direction of the line is given by the numbers that multiply t. 8, 5, minus 1. The line will be parallel to the plane if and only if those are perpendicular, which means if and only if their dot product is 0. So you just take v dot n, and oh, it's minus 12. It's not 0, so the plane is not parallel to the line. It will intersect somewhere. Let's go down to this one. I'm going to come back to that one. Let's see. No, let's do this one. Suppose I want to find. No, not that one. Sorry. Distance between a point and a plane. Here's a nice theorem. It's ax0 plus by0 plus c0 plus d absolute value divided by the square root of a squared plus b squared plus c squared is the distance from a point to a plane. How can you derive that one? This is kind of hard to memorize. An alternative is to instead do this. A lot of these formulas, if you don't memorize them, you can still figure them out. You can take any point you want on the plane. I'm given a plane. I could just put in, for instance, x equals 0, y equals 0, and then I just find, oh, z must be minus d over c. So I find a point on the plane immediately, no matter what plane it is. Just put in two of the numbers 0 and find out what the other one is. Now that's point P. If I take the point off the plane, Q, I want to find the distance from Q to the plane. What do? Well, I can take the vector PQ. Its projection onto the normal to the plane is this vector here. Then the vector that's perpendicular to the plane going up to the point, its length is the distance. So all you have to do is take the length of the projection from a point on the plane to the point in question onto the plane's normal, which is easy to compute. Projection of PQ onto N gets you the distance. Well, if you work this out, what you'll find out is it's this formula. So you memorize the formula, or you say, oh, it's the length of the projection of PQ onto N. That's pretty easy also. So I just wanted to point that out. That some of these formulas, it's easier to, easier just to remember something else. So there's the derivation there. This is a useful problem here. I wonder what the angle of intersection is between two planes. Oops. Here's a plane and here's a plane. How can I compute it? Here's how we do it. I think this write-up could use a little illustration. If I want the angle between this plane and this plane, what I do is I construct their normals. Here's N1, normal to the first plane, and here's N2, the normal to the second plane. And the angle theta between the plane, we call it the smaller of the two angles. You can say maybe it's this angle. We take it as the angle between 0 and 90 degrees. Here's the angle between the two planes. There's also the angle between the normal vectors. So what we can do is say that I know how to find the angle between two normal vectors, n1 and n2. It's the inverse cosine of n1 dot n2 over length of n1 n2. This isn't simpler, but memorized that one, this one. So it's simple in the sense we don't have to memorize anything new. We can compute that. But if you get an angle bigger than 90 degrees, you have to subtract it from 180 because, right, then you're getting this angle instead of this one. Actually, it comes out, if the dot product is negative, that it's an obtuse angle, you recall. If the dot product is positive, it's an acute angle. So all you have to really do is put an absolute value here, and this automatically computes the angle between the two planes. We just derived the formula. So sometimes it's easier just to memorize, oh, I just need the angle between the two normal vectors, or that minus 1 taken from 180, rather than memorize this formula, which I find hard to remember. So some of these things, you'll find an easier way to memorize them. So in this case, if I have a plane 2x minus 4y plus 4z equals 6, and 6x plus 2y minus 3z equals 4, how do I know they're planes? They're ax plus by plus cz equals d. That's automatically a plane. That's the standard form, except the book puts d on this side. So it's standard form with d on the other side. Given those two planes, I can find the angle between them because immediately I know the normals. 4 minus 4, 4. Remember, you can read it off. 6, 2 minus 3 are the normals. There they are. Now I just take the cosine of the angle. The angle between them is n1 dot n2 over length of n1, length of n1, length of n2. And then put absolute value to make sure I get an angle between 0 and 90. There it is. I get 4/21 for this one. Our cosine of 4/21 are 79 degrees. Okay, here's an interesting one too, finally. The equation for the line of intersection between two planes. So I said these sections are kind of easy, but there's actually a whole lot of different kinds of things to do with planes. You know, are they parallel? What's the angle of intersection? What's the distance? And finally now, what's the line of intersection? Well, if you compute the cross product of the normals, what do you know about that? That is a vector that lies in the intersection of the two planes. Let's see if I can put this back up. Oops. So a lot of this, it really helps if you can visualize a little bit. If I want the line of intersection, I always think this. If I want a line, I find a point and a vector in the direction of the line, then I can write down those parametric equations immediately. If I want a plane, I look for a point and a normal of the plane. I write down the point normal form immediately. So I'm thinking, how do I get a vector that's in the direction of the line? If you kind of imagine the two planes intersecting, well, the normal to one and one cross product with the normal to the other and two is going to be the right by the right hand rule, perpendicular like that, and it's going to have to be in the intersection of the two planes. Since it's perpendicular to both planes, it has to lie in both planes. Perpendicular to both normals has to lie in both planes. So here's the vector v that goes in the direction of the line. It's just n1 cross n2. And then I just need any point in the intersection. It just says almost intersect the xy plane. Z equals 0, since 0, 0, 1 is on the plane. Substitute z equals 0 into both planes yields these two equations, right? So in both planes you put z equals 0. Now you've got two equations and two unknowns, and you can solve those for x and y and get an x, y, z that lies in both planes. So just put z equals 0 in both planes, providing that they intersect the xy plane. Now you get x equals 1 and minus 1 in the, for the other two coordinates by solving these two equations. So 1 minus 1, 0 is a point on the plane. We found out that 4, 30, 28 is a vector normal of the plane. So here's the vector parametric form. X, y, z equals the vector to the point plus t times the direction vector. And you could also write parametric equations: x equals 1 plus 4t, y equals minus 1 plus 30t, z equals 0 plus 28t. Try the problems now, see if you have any difficulties.